Hello guys, and welcome to another video here on pre-security, and we're currently treating network fundamentals, and this particular video we are focusing on packets and frames. So let's get right into it. Now, packets and frames. Alright, this is the walkthrough video. We're gonna skip that. Now, task 1. Basically, let's go over what we're looking at here. Packets and frames. Understand how data is divided into smaller pieces and transmitted across a network to another device. Okay. All right. Now, task 1. What are packets and frames? Now, packets and frames are small pieces of data that, when forming together, make a larger piece of information or message. However, there are two different things in the OSI model. A frame is at layer 2, which should be the link. Now, the data link layer, exactly, meaning there is no such information as IP addresses. Now, think of this as putting an envelope without an envelope and sending it away. The first envelope, think of this as putting an envelope within an envelope and sending it away. The first envelope will be the packets that you mail, but once it is opened, the envelope within still exists and contains data. This is a frame. Okay. Now, the process is called encapsulation, which we discussed in room 3, the OSI model. Now, at this stage, it is safe to assume that when we are talking about anything IP addresses, we are talking about packets. When the encapsulating information is stripped away, we are now talking about the frame itself. Makes sense? Okay. Now, packets are an efficient way of communicating data across networked devices, such as those explained in task 1, because this data is exchanged in small pieces. All right, there's less chance of bottlenecking occurring across a network when large messages being sent at once. All right. Now, for example, when loading an image from a website, the image is not sent to your computer as a whole, but rather small pieces where it is reconstructed on your computer. Now, take the image below as an illustration of this process. The cat's picture is divided into 3 packets where it's reconstructed when it reaches the computer to form the final image. So the web server sends it in 3 packets, 1, 2, 3, and then when it gets to your computer, it reconstructs and gives you the final image. Great. Now, packets have different structures that are dependent upon the type of packet that is being sent. Okay, different structures. All right. As we will come on to discuss, networking is full of standards and protocols that act as a set of rules for how the packet is handled on a device. Okay. Now, with the internet predicted to have approximately 50 billion devices connected by the end of 2020, that's already happened, things quickly get out of hand if there is no standardization. All right. Now, let's continue with our example of the internet protocol. A packet using this protocol will have a set of headers that contain additional piece of information to the data that is being sent across a network. Now, some notable headers include the header and the description, of course, the time to leave. Yes, this is very, I had it. Now, this field sets an expiry timer for the packets not to clog up your network if it never manages to reach a host or escape. All right, so it won't be bugged up on your network. Checksum. This field provides integrity checking for protocols such as TCP/IP. If any data is changed, this value will be different from what was expected and therefore corrupt. So checksum checks to make sure that the packets that you receive are all complete, and whatever you get as your data is a complete data. So checksum is a very good header that attached to it. So source address. Now, the IP address of the device that the packet is being sent from, so that the data knows where to return it to. Okay, where to return to. Okay, destination address, the device's IP address the packet is being sent to, so that the data knows where to travel next. Okay, great. Now, what is the name of the piece of data when it does have IP addressing? When it does, then we're looking at packets. All right, and then what is the name packets? Let me see. Great. Now, what is the name for a piece of data when it does not have IP addressing? Now we're looking at frame. frame. All right, great. Now let's head on to task 2. All right, task 2, TCP/IP, the three-way handshake. Okay, now TCP, or the Transmission Control Protocol for short, is another one of these rules used in networking. Now this protocol is very similar to the OSI model. I think it's best to say this is the practical OSI model. All right, TCP is the one we use, or ASI model is like the standard. All right, now the protocol is very similar to the OSI model that we have previously discussed in room 3 of this model so far. All right, now the TCP/IP protocol consists of 4 layers and is arguably just a summarized version of the OSI model. So these layers are application transport, internet, and network interface. Okay, application transport, internet, and network interface, and some people might call it application transport, network, link, physical. Just the difference might just be there's no presentation and session. But here on Tryhackme, it's the summarized version is called application transport. Then it becomes internet and network interface. Now let's head on. Now, very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data, or packet, transverses it. As you may recall, this process is called encapsulation, where the reverse of this process is decapsulation. Now, one defining feature of TCP is that it is connection based, which means that the TCP must establish a connection between both a client and a device acting as a server before data is sent. All right. Now, because of this, TCP guarantees that any data sent will be received on the other end. Now, the process is named the three-way handshake, which is something we'll come on to discuss shortly. A table comparing the advantages and disadvantages of TCP is located below. We've seen that before. Well, now, the advantage, 1, guarantees the integrity of data. Make sure that you get the exact that nothing is missing. And then the disadvantage is that it requires a reliable connection between the two devices. So if one small chunk of data is not received, then the entire chunk of data cannot be used and must be resent. Okay, that's one of the disadvantages. Yeah. Now, advantage number 2 is capable of synchronizing two devices to prevent each other from being flooded with data in the wrong order. Now, the second disadvantage is that a slow connection can bottleneck another device, as the connection will be reserved on the other device the whole time. All right, making other connections to wait, I guess. Right, now the third advantage of the TCP model is that it performs a lot more processes for reliability. In order to ensure this reliability, a lot of processes has to be performed. Now the disadvantage here, which is the last one here, is this TCP is significantly slower than UDP because more work, which is computing, has to be done by the devices using this protocol. All right, great. Now TCP packets contain various sections of information known as headers, and that are added from encapsulation. During the encapsulation process, different headers are added. All right, now let's explain some of the crucial headers in the table below. Now, the first one we're looking at here is the source port. What's the source port? Now, the value is the port opened by the sender to send its TCP packet from. Now, the value is chosen randomly out of the ports from 0 to 65535 ports, all right, or 65,535 that ends already in use at the time. So the source port is the one that will be created when the sender is about to send the packet, and it chooses these ports from between 0 and 65535, considering if any of these ports is not being used at that point in time. Now, the second header here is the destination port. The value is the port number that an application or service is running on the remote host, that is the one receiving data. For example, a web server running on port 80, unlike the source port, the value is not chosen at random. So it has to be specific, like where are you sending this to, what destination port is receiving it. Now, the source IP is the third header we are discussing. Now, this is the IP address of the device that is sending the packet. So, the IP address, Internet Protocol. Now, destination IP, this is the IP address of the device that the packet is being destined for. All right, that's quite simple. Now, sequence number. All right, what's this? Now, when a connection occurs, the first piece of data transmitted is given a random number. We will explain this more in depth further on. Okay, so the first data has a number, which is a sequence number. Now, acknowledgement number. After a piece of data has been given a sequence number, the number for the next piece of data will be the sequence number plus 1. We'll also explain this more in depth. So the acknowledged number might be the sequence number plus 1. Okay, I see. Now, checksum. What's checksum? Now, the value is what gives TCP integrity. This is very important, the checksum. A mathematical calculation is made where the output is remembered when the receiving device performs the mathematical calculation. The data must be corrupt if the output is different from what was sent. So more like something is calculated from the beginning and saved, then when the output gets set, it recalculates, and if it doesn't match with the first check, then the data is corrupt and it has to be resent. Now, data, this header is where the data, that is bytes of file that is being transmitted, is stored. Now, lastly, the flag. This header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors, which is what we'll come to explain below. Okay, let's understand what the flag is. Now, next, we'll come to discuss the three-way handshake, the term given for the process used to establish a connection between two devices. Now, the three-way handshake communicates using a few special messages. The table below highlights the main ones. Now, let's go. Step 1 to hash. Okay, now message and the description. Now, the first one is SYN, or the SYN. A SYN message is the initial packet sent by a client during the handshake. Now, this packet is used to initiate a connection and synchronize the two devices together. We'll explain this further later on. Okay. Now, the SYN-ACK message, or the SYN/ACK. This packet is sent by the receiving device of the server to acknowledge the synchronization attempt from the client. So, hello, hi, kind of thing. Now, acknowledgement. These acknowledgement packets can be used by either of the client or server to acknowledge that a series of message/packet has been successfully received. All right. Now, data. Now, once a connection has been established, now data such as bytes of file is sent via the data message. All right. Then FIN. This packet is used to cleanly or properly close the connection after it has been complete. So when everything's said and done, when the data has been sent, the FIN is used to close the connection. Now, RST, which is the last one, which is step hash. Now, this packet abruptly ends all communication. This is the last resort and indicates there was some problem during the process. Okay, reset is more like if there's an issue during the process. Okay, for example, if the service or application is not working correctly, or the system has faults such as low resources, the RST is the message, is the packet that will abruptly end all the communication. Now, the diagram below shows a normal three-way handshake process between Alice and Bob in real life. Alice and Bob. Now, in real life, this would be between two devices. Alice sends a SYN message. Bob sends a SYN-ACK message to acknowledge the message has been sent, and Alice sends an acknowledge to confirm that message was received. All right, and note that this acknowledgement can be sent by either Alice or Bob at any time, just to acknowledge the message has been sent. Now, any sent data is given a random number sequence, and is reconstructed using this number sequence and incrementing by 1. Both computers must agree on the same number sequence for data to be sent in the correct order. Now, this order is agreed upon during three steps. Okay. Now, SYN, the client, SYN client will now be here's my initial sequence number ISN to synchronize with 0. Now, SYN-ACK acknowledgement or SYN-ACK, the server will now respond, here's my initial sequence number ISN to synchronize with 5000, and I acknowledge your initial sequence 0. All right, now acknowledgement by the client will now be I acknowledge or I hack your initial sequence number ISN of 5000. Here is some data that is my ISN plus 1, 0 plus 1. That will be like the next message you're getting. So it's more like, let's see this here. An example would be client or with the sender with initial sequence 0, final number sequence 0 plus 1, 1. Client sender 1, final sequence 1 plus 1, 2. Client sender 2, initial sequence 2, it will now be 2 plus 1, 3, and so on. Alright, now TCP closing a connection. Let's see what that is. Now, let's quickly explain the process behind TCP closing a connection. First, TCP will close a connection once a device has determined that the other device has successfully received all the data. Now, because TCP reserves system resource on a device, reserves a system resources on a device, it is best practice to close TCP connection as soon as possible. To initiate the closure of a TCP connection, the device will send a FIN packet to the other device. Of course, with TCP, the other device will also have to acknowledge the packet. Now, let's show this process using Alice and Bob as we have previously. Okay. Now, here we have Alice will send a FIN to close the connection. Bob will send an acknowledgement and a FIN to. Then Alice will close it on acknowledgement. Okay. Now, in this illustration, we can see that Alice has sent Bob a FIN packet because Bob receives this. He will let Alice know that he received it and that he also wants to close the connection. That is why we have the second FIN here. Alright, now Alice has heard Bob loud and clear and will let Bob know that she acknowledges this. Okay, alright, great. Now, what is the header in a TCP packet that ensures the integrity of data? We're looking at checksum. Checksum is what determines that integrity. Now, provide the order of a normal three-way handshake with each step separated by a comma. Alright, first we have sin, then we have sin/hack, and then we have sin. Okay, comma, sin. What am I getting wrong? Let me see. Okay. Sorry, not sin, hack. I'm sorry. What is happening? Sin, hack. Okay, what else am I doing here? Okay, I got it. Now, let's head on to task 3. Here on task 3, we have a practical handshake. Now, let's open the site quickly while I read that. Okay, help Alice and Bob communicate by reassembling the TCP handshake in the correct order, and in the static lab attached to the stacks, which we're going to see here now. And enter the value of the flag given at the end of the conversation in the question below. So what is the value of the flag given at the end of the conversation? Let's start. So sin, fin, hack. We're starting with sin, of course. Can you hear me, Bob? And Bob will be like, yes, I can hear you. Not this. Okay. Now, once this has been acknowledged, then the sender will be like, okay, great. Now he has to send like a packet, I guess, or a message, a data. So cheesecake is on sale, and acknowledgement that I saw that, I hear you, and then okay, I'm all done. All right, I'm all done, and then yeah, me too, and then okay, goodbye. Oh, okay. All right, so we got that. All right, we're done with task 3. Now heading to task 4 here. Now the user datagram protocol, UDP, all right, is another protocol that is used to communicate data between devices. Unlike its brother TCP, UDP is a stateless protocol that doesn't require a constant connection between the two devices for data to be sent. Okay, for example, the three-way handshake does not occur, nor is there any synchronization between the two devices in UDP. the user data protocol, user datagram protocol. All right. Now recall some of the comparisons made about these two protocols in Room 3 OSI model. Yes, namely UDP is used in situations where applications can tolerate data being lost in pixels, for example, like in video, such as video streaming or voice chat, or in scenarios where an unstable connection is not the end all. Okay, now a table comparing the advantages and disadvantages of UDP is located below. Okay, the first advantage of UDP here is that UDP is much faster than TCP, of course. Now the disadvantage is that UDP doesn't care if the data is received or not. Okay, so some data can be lost and it doesn't care. All right, now UDP leaves the application user or software to decide if there is any control over how quickly packets are sent. Okay, UDP leaves the application or the user software to decide if there's any control over how quickly packets are sent. That's an advantage. Now, the disadvantage is that it's quite flexible to software developers in this sense, of course. Now, UDP does not reserve a continuous connection on a device as TCP does. It doesn't have a reserved connection. Now, this means that unstable connection results in a terrible experience for the user. Okay. Now, as mentioned, no process takes place in setting up a connection between two devices, meaning that there is no regard for whether or not data is received, and there are no safeguards such as those offered by TCP, such as data integrity. Okay, now UDP packets are much simpler than TCP packets and have fewer headers. However, both protocols share some standard headers, which are what is annotated in the table below. Header, the first is the time to leave, TTL. Now this field sets an expiry timer for the packet, so it doesn't clog up your network if it never manages to reach a host or escape. Now, source address. Now, the IP address of the device that the packet is being sent from, so that the data knows where to return to. Destination address is the device's IP address the packet is being sent to, so that the data knows where to travel next. All right. Now, the source port here is this value is the port that is opened by the sender to send the UDP packet from. This value is randomly chosen out of the ports from 0 to 65535 that ain't already in use at the time. Okay. Now the destination port, this value is the port number that an application or service is running on the remote host. In terms here, we're talking about the one receiving the data. For example, a web server running on port 80. Unlike the source port, this value is not chosen at random. It has to be specific. All right. Now, data. This header is where data, that is bytes of file that is being transmitted, is stored. We see the similarities, just that the difference here is now those other additional headers where they have to confirm the integrity, checksum, fin, reset, and all that. Okay, now next we'll come on to discuss how the process of connection via UDP differs from that of something such as TCP. We should recall that UDP is stateless. No acknowledgement is sent during a connection. All right. Now, diagram below shows a normal UDP connection between Alice and Bob. In real life, this would be between two devices: Alice, Bob. Bob request, Alice response, and so on and so forth. Or it could be Alice sending a request, Bob response. Okay, what does the term UDP stand for? We're looking at user datagram protocol. And what type of connection is UDP? Stateless. What protocol would you use to transfer a file? We're looking at TCP because I don't want to lose anything in the file and I want to confirm. I need some kind of integrity here. Now, what protocol would you use to have a video call? UDP because I want it fast and I don't mind losing some pixels. All right, great. We're done with task 4. Let's head on to task 5. Here is a practical for ports 101 practical. All right, now let me open the site while it loads, while I try to, let me see. Okay. It takes time, but let me just cover this quickly, or let me just head on to this area. Let me see. if it does. Okay, let's just quickly do this now. Perhaps aptly titled by their name, ports are an essential point in which data can be exchanged. Let me see. Oh no. Let me see. Same thing. All right, I'll just use this last one like as if I knew, so I prepared already, because it always gives me issue. Okay, now let's quickly run this. Now, perhaps aptly titled by their name, ports are an essential point in which data can be exchanged. Now, think of a harbor and port. Ships wishing to dock at the harbor will have to go to a port compatible with the dimensions and the facilities located on the ship. So when the ship lines up, it will connect to a port at the harbor. Now, take for instance that a cruise liner cannot dock at a port made for a fishing vessel and vice versa. Okay, it has to be compatible, let's say, or it has to fit. Now, this port enforces what can park and where. If it isn't compatible, it cannot park here. Now, networking devices also use ports to enforce strict rules when communicating with one another. Now, when a connection has been established, recalling from the OSI model room, any data sent or received by a device will be sent through these ports. In computing, ports are a numeric value between 0 to 65,535 ports that are available. All right, now, because ports can range from anywhere between 0 to 65,535, they quickly runs the risk of losing track of what application is using what port. Okay, so a busy harbor is chaos. Thankfully, we associate application softwares and behaviors with a standard set of rules. For example, by enforcing that any web browser data is sent over port 80, software developers can design a web browser such as Google Chrome or Firefox to interpret the data the same way as one another. Now, this means that all web browsers now share one common rule. Data is sent over port 80. How the browsers look, feel, and easy to use is up to the designer or the user's decision. Okay. Now, while the standard rule for web data is port 80, a few other protocols have been allocated a standard rule. Now, any port that is within 0 and 1024, good, this has appeared, 0 and 1024, which is 1024, is known as a common port. I call it like special ports. Let's explore some of these other protocols below. Protocol, the port number, and the description. And one of the popular one is the file transfer protocol, FTP, runs on port 21. Now, this protocol is used by a file sharing application built on a client-server model, meaning you can download files from a central location. Secure Shell, SSH, is on port 22. This protocol is used to secure login to systems via a text-based interface for management. All right. Hypertext Transfer Protocol, HTTP, runs on port 80. HTTPS runs on port 443, and they have similarities. Here is that the protocol powers the World Wide Web, www. Your browser uses this to download text, images, and videos of web pages. And in case of the HTTPS, which is the Hypertext Transfer Protocol Secure, runs on port 443, and this protocol does the exact same thing as the HTTP, which is for the World Wide Web protocol. Okay, however, securely using encryption. Okay, now the other one is Server Message Block, SMB. It runs on port 445. Okay, this protocol is similar to the File Transfer Protocol, FTP. However, as well as files, SMB allows you to share devices like printers. All right, now the last here is Remote Desktop Protocol, RDP. That's the first time I'm hearing this one. It runs on port 3389. This protocol is a secure means of logging into a system using a virtual desktop interface, as opposed to the text-based limitation of the SSH protocol. Okay. So it's compared to the secure shell. Okay. All right. Now, we have only briefly covered the more common protocols in cybersecurity. So you can find a table of the 1024 common protocol list for more information. I'll open that later. Now, what is worth noting here is that these protocols only follow the standards. That is, you can administer applications that interact with these protocols on a different port other than what is the standard, running a web server on 8080 instead of 80 standard ports. Note, however, applications will presume that the standard is being followed, so you will have to provide a colon along the port number. Okay. Now the practical challenge: open the site attached to this task. We've already opened it, and connect the IP address 8888.8.8.8 on port 1234, and you will receive a flag. Okay, that will be pretty easy. But before that, let's see the list of all the ports here. Let me zoom in a little bit. So we have 0 TCP reserved, 0 UDP reserved, 1 TCP, UDP. Whoa. Okay, but the difference here is the keyword here is what they use for echo and discard and so on. I think I might just start this page. This is very important. Okay, and so on and so forth. All right, that's a lot. That's quite a lot. Yeah, of course. All right, I want to see the AT, UDP, HTTP. World Wide Web. Okay, actually, this is where I'm supposed to be looking at this particular things. Remote job service file 42. Let's see that 42. Hostname server. Okay, great. All right, enough of that, and let's play this last one here. What is the flag received from the challenger? We are using 8.8.8.8, and port, we're looking at port 1234, and then we have to connect. Boom. Connection received. Tryhackme, you're connected to a port, correct? And with that being said, we're done with tax 5, and let's hop on to the last tax here, tax 6. On tax 6, yeah. Now continue your learning, extending your network. Now join the final room of the networking model. Extend your network to continue your learning and complete this model. Okay. Now answer the question. Terminate the static site lab deployed in task 3 and 5. Terminating that, and join the extending your network room. Okay, completed. And that's that for the end of this room here. Thank you for watching. Thank you for learning with me. I'll see you guys in the next room, and then do have a lovely day. Ciao.